Alright, this is Notes Video 8C, and we're covering pages 260 through 263. In my last video, I got cut off because I ran out of time, so we have to go back to example 8.3. This is on page 260, and example 8.3 says, a chemist needs to find an element that readily gives up an electron. So let's stop and think about that for a minute. If it readily gives up an electron, it needs low energy because it's easy to do it. So it needs a low ionization potential. So which has the lowest ionization potential? Which would suit the chemist's needs best? Ca, As, or Br? Looking at the periodic table, Ca is in column 2A, As is in column 5A, and Br is in column 7A. So which would most easily give away its electrons? That would be Ca, because Ca only has 2 valence electrons, so it would really like to get rid of those outer 2. That would be the most easiest way to come up with an ideal electron configuration. And remember that starting on the left has lower ionization potentials, so that would make sense. That would be Ca. And the second part of 8.3 says, which of the following holds on to its electrons the tightest? Okay, and we're looking at column 3A. We have aluminum, or below that is In, whatever that element is, or above that is B, boron. So which atom would hold on to its electrons the tightest? Well, we talked about the size, how the size makes a difference. So the smaller that the atom is, the closer the valence electrons are to the positive charges of the protons, and they're going to hold on more tightly to those valence electrons. And the smallest atom is boron. So boron would hold on to its outer electrons the tightest. So that's example 8.3. And now we're going to move on to our second periodic property, which is electronegativity. Electronegativity is a measure of how strongly an atom attracts extra electrons to itself. Okay, so how strong is the atom attracting extra electrons? Again, if we look at the periodic table, the atoms that are most strongly going to be trying to get just one more little electron would be over here in column 7A. They would very strongly attract one extra electron. They want that one extra electron to have an ideal electron configuration of 8 outer valence electrons so that they're full, so that they're satisfied. So on the right-hand side of the periodic table, electronegativity is the strongest. Over here on the left-hand side of the periodic table, these atoms don't really want to attract more electrons. They're more interested in giving away their valence electrons because they only have 1, 2, or maybe 3. So they would rather give away their outer electrons. They would not be attracting more. Okay, so for electronegativity, you can find this on figure 8.2. Okay, if this is our periodic table, as we move from left to right, electronegativity increases. So my arrow here is showing you that as we move across the periodic table in this direction, electronegativity is increasing, meaning electronegativity would be lower on this side and higher over on the right. Okay? As we move down the periodic table, what does electronegativity do? Remember that as we move down the periodic table, atom size is getting bigger. So the outer valence orbitals and outer valence electrons are farther away from that positively charged nucleus. So as we move down the periodic table, there's less attraction between the outer electrons and the inner protons. So as we move down, electronegativity decreases. If we have a really big, quote unquote, big atom, because atoms can't have a really big, right? But if we're at the bottom of the periodic table and our atom is relatively large, it's going to have low electronegativity because there's so much space between the positive protons and the negative electrons. If we're talking about a smaller atom, at the top, electronegativity is going to be greater, because the protons are closer to those outer valence electrons, and so they have more attraction, more pull. All right, so that's the second periodic property. The third is atomic radius. Okay, and that would be the radius of the atom, the size of the atom. Okay, and we're going to write that atomic radius increases, we'll write this one out, increases from top to bottom of periodic table. And we've already talked about why that is, because as we move down the periodic table, the atom size gets bigger because we're adding more and more electron orbitals. Okay, now this is interesting. Atomic radius decreases from left to right of the periodic table. Now, why would that be? Why would the size get smaller as we move across the periodic table? Well, remember, as we move across the periodic table, we're adding more protons to the atom, more protons to the nucleus. So the more protons we have, the greater the positive charge in the center of the atom. And if that positive charge in the center of the atom is bigger, it's going to attract those outer valence electrons just a little tiny bit more, and so those outer electron orbitals are going to get sucked into the center a little bit more, making the atom a little bit smaller. So interesting. Okay, so atomic radius decreases from left to right. Here's our periodic table. As we move from left to right, atomic radius decreases. As we move from top to bottom, atomic radius increases. All right, so you guys are going to have to know these periodic properties and understand them and have them memorized. So make sure that you let me know if you have any questions. Come to class with your questions or email me.